Okay, well, let's get started. First of all, thank you for coming out in the dead of winter in the blizzard. It's not really a blizzard, come on, it's like a couple inches, but it's still fun and exciting to have a snowstorm. So thank you for plowing through the snow to come out. I hope you're going to be happy you did, because by the end of class today, you will be a training example. And the point of today's class is to talk about our first Bayesian classifier. And before I do that, I just want to kind of remind you a quick review from last time. The main point of the last lecture was really that estimating probabilities from data, or learning probability terms from data, I don't care whether you use the verb estimate or learn, it's the same thing, is really central to any kind of probabilistic approach to machine learning. And there are, in fact, two principles by which we try to estimate probability parameters from data. Those are maximum likelihood estimates, is one principle, which says that we want to choose the parameters theta, that's what we're trying to learn, in a way that maximizes the probability of the data, given theta. The second principle, which is very much like that, says, well, actually we want to choose the theta which is itself most probable given the data. And we know by Bayes' rule that this quantity equals this quantity. That's what Bayes' rule says. And if you look at this, you notice that, well, the denominator doesn't really depend on theta, so we can ignore that. So choosing the theta that's most probable is choosing the theta that maximizes the numerator here, which, if you look at that numerator, is just like maximum likelihood estimation, except that we also have a prior probability on theta. And so the idea of map estimation is that it gives us a chance to bring in some prior knowledge that we do have, or prior assumptions that we do have about the value of theta, and express them as p of theta. Then we looked at we took as a case study the problem of estimating theta for a Bernoulli distribution, that is a coin flip, where we say, well, we have a random variable which could turn out to be heads or tails, 1 or 0, and we'll just say, depending on the coin, there's some theta, which is the probability that that coin will turn out to be a heads, x equals 1. And so we said, okay, then each flip of the coin yields a Boolean value for x. If we flip it a bunch of times, we can count the number of ones and zeros, heads and tails, in that collection of independent flips which are identically distributed. Identically distributed just means they're all following the same theta, it's the same coin. And they're independent in the sense that the outcome of one coin flip doesn't really influence the outcome of the next coin flip. And so it was easy for us to write down an expression for the probability of the data. If we observe alpha 1 heads and alpha 0 tails, then it's just theta times the number of heads, and 1 minus theta, of course, that's the probability that we'll get a tails, times the number of observed tails. That's just the probability that we'll get for a collection of alpha 1 heads and alpha 0 tails. And then we found that when we did a little bit of calculus to solve for what is the value of theta that makes this the greatest, given that we know what alpha 1 and alpha 0 are, then we found out it was just this. So if we flip the coin and we end up with 3 heads, 7 tails, then our maximum likelihood estimate is just 3 out of 10, which happily matches our own intuition about what common sense would tell us. But now we know that it actually follows this principle, that it's also the value of theta that maximizes the probability of the observed data, the alpha 1 and alpha 0. And by the way, this term here is often called the data likelihood. It's so important that it gets its own name, but it's really just the probability of the observed data given theta. Then we also talked about a second way of doing this, the map estimate. And again, we illustrated this in the case of a coin flip and worked through the arithmetic on that. Actually, the arithmetic was remarkably similar. In this case, again, the probability of the data, of the observed data given theta is just as it was before. But now, in this case, since we're doing a map estimate, we want to also include a prior on theta. And in the case last time, we agreed that we would use a prior that's of this form. It's called a beta distribution. It takes itself two parameters, beta 1 and beta 0. And it gives the probability for any theta to be equal to this quantity. The prior probability on theta is this quantity. And you can choose different values of beta 1 and beta 0 to get different values for the probability of theta. But, and after class, somebody asked me, what is this B function here? Sorry, I didn't have time to mention that last time, but the B function is just a normalization. Remember how if we have a probability distribution, the probability has to sum to 1. Or in the case of a continuous distribution, this is actually a continuous distribution because theta can be any real number. In that case, the integral under the probability density function has to integrate to 1. It's the same idea. And what this B function here is just some quantity that makes sure that the integral under this area, this is equal to the integral under this expression. And so this makes sure that the integral actually does end up being 1 because we just normalize by it. So for our purposes, we can just think of this as a normalizing constant that makes sure the integral over all possible values of theta of the probability equals 1. And of course, that constant doesn't even depend on what theta is. And so when we're solving for theta, we can just ignore that constant if what we're going to do is to try to maximize the probability. Okay, so there was our form of prior, and we chose that on purpose to have a particular form. It's called actually the conjugate prior for this multinomial distribution, this binomial distribution that we have. We chose it because this quantity, this part here, looks a whole lot like the form of the data likelihood here. And so when we multiply those together, remember what we're going to do now to find our map estimate is find the theta that maximizes the product of the prior and the data likelihood. And when we multiply those together, we get this nice expression where this quantity and this quantity go together so that we end up with a theta to alpha 1 plus beta 1 minus 1 times a 1 minus theta times an alpha 0 and a beta 0 minus 1. So that actually gives us something of the same kind of form. And so then, not surprisingly, when we maximize this by picking the theta that maximizes it, we got something that looks just like the MLE estimate, except with some hallucinated additional imaginary heads and tails added in. The reason this looks so much like the MLE estimate is because basically the mathematical form of this times the data likelihood is just very similar to that data likelihood expression itself, except that alpha 1 here, for example, is now replaced by alpha 1 plus beta 1 minus 1. And so that's why it shows up here instead of just this, as we saw in the maximum likelihood estimate. Okay, so there's some nice mathematics there that, again, tells us that if we want to assume this kind of a prior on the probability parameter that we're estimating for our coin, then what it means to choose the theta that's most probable given the data, which is the same as choosing the theta that maximizes this, because this is the numerator for Bayes' rule, is in fact this. And we discussed, before we even went through the math, we discussed how this is a very intuitive way, very nice way of bringing in prior information, because if we're very certain about our priors, for example, this is a coin I know well, and I'm pretty sure that it's a 0.5 probability, then I can choose very large values for beta, like 1,000 and 1,000 and 1,000 for beta 1 and beta 0, make them equal and make them big. Then it would take a lot of observed real data, alpha 1 and alpha 0, to outweigh my prior. But if I'm not very sure, then I could choose a very small number, like beta 1 equals 2 and beta 0 equals 2, which would effectively give me just 2 minus 1, just one hallucinated example. And so then I'm going to rely a lot more on the observed flips, the alphas, to give me the final estimate. So that's one thing that's nice about this beta prior. It effectively lets us choose both the ratio, beta 1 to beta 0. I just chose 0.5, 0.5, but I could have chosen 0.9, 0.1 if that was my prior. But it also lets me say how strongly I want to rely on that prior when I calculate the final answer. And that's a matter of what quantity of hallucinated examples I introduce in addition to what ratio I use for beta 1 to beta 0. So that's very nice form. And as we discussed last time, has the property that if you flip the coin, just keep flipping it forever, asymptotically as you get more and more coin flips, the alphas just completely dominate. And as the number of coin flips goes to infinity, you notice it didn't really matter what you chose for beta 1 and beta 0. They're going to be swamped out eventually to be inconsequential to decide the final ratio. It also has this nice property that if you have enough observed data, it doesn't really matter what your priors were. Yes?
I know that it doesn't have any kind of effect on our estimation, but just for the sake of completeness, shouldn't we have something like choosing alpha 1 from alpha 1 plus alpha 0 options in the P of the probability of D given theta?
Choosing alpha from?
Success, for example, from 10 experiments. So when we are saying like that, it's like, so I mean, we can have the combinations of them, right? Choose different successes.
Oh, 3 different experiments, you mean?
No, I mean, we have 10, for example, flipping of the coin. But these 3 successes can be any one of them, right?
Oh, alpha 1 takes into account the entire experiment. So if we have 10 flips of the coin, alpha 1 is how many of those flips were heads. See, so alpha 1 is not about a single flip. It's about if we do n flips, alpha 1 is the number of times that out of those n flips that we ended up with heads. So it might be if we flip 100 times, alpha 1 could be 43.
I mean, so we are trying to find out the probability of D given theta, right? The first equation. So we are saying that this is equal to theta powered by alpha 1, 1 minus theta something. So we are assuming that in this case we have alpha 1 success, right?
Alpha 1 heads, x equals 1s.
So I mean, this alpha 1 number of successes can be among this, the whole, the whole experiment, right?
Yes,
so
yes.
You can have a combination of alpha 1 plus the whole experiment in that equation too.
I think maybe we should take this offline because alpha 1 is really a property of the entire experiment. It's not the property of a single flip. And so, if we flip 1,000 times, alpha 1 will be the number of times out of 1,000, the total number of hits. So let's take, maybe I'm not understanding exactly the question here. Okay, so the reason I'm reviewing this is this really matters. It matters for the homework, as you might have noticed. Hopefully you've noticed. And it also matters for the course because we're going to talk about, well, we're not going to talk about coin flips very much more in this course, but we are going to talk about Bayesian classifiers and Bayesian learning methods. And for all of those, it turns out that the learning procedure will turn out to involve estimating some probability parameters. And we're going to come back. You'll be good friends with map estimation and MLE by the end of the semester because you'll see them over and over as these principles that we use for a very diverse set of learning, probabilistic-based learning methods that we derive in the course. Okay, so let's go on to our first one then. Here's some data we looked at before. And we used this data before to talk about how we could estimate the parameters of the awesome joint distribution over a set of variables. Today I want to talk about, well, if we're trying to learn some function or some probability distribution, let's say we're interested in learning the probability distribution for wealth given gender and hours worked, then, well, we could estimate the whole joint distribution, of course, and then calculate this from it. Or we could try to estimate just the conditional distribution directly and forget about estimating the joint distribution, right? So, in fact, if the only thing I care about is this conditional probability, let's predict wealth from gender and hours worked, then I could just try to learn this shorter table, which tells me the probability that I'll be rich or poor, depending on the 4 possible values for gender and hours worked. Okay, so you can see that. Well, maybe you can't see, because it looks like there are 8 numbers we have to estimate here, and there are 8 numbers here, too. So maybe it doesn't matter. But actually, it does. How many of these numbers, how many of these parameters that we'd like to know in order to perfectly characterize that distribution, how many of these are actually calculatable from others that are here? 4, right? Because notice the probability that you're rich, given G and HW, some value of that, is just 1 minus the probability that you're poor. These 2 numbers have to sum to 1, and in fact they do in every case. So really here we have to estimate 4 parameters. For example, we could estimate these 4, and then these we can just calculate. The second column we can just calculate as 1 minus these. What about up here? I have 8 numbers. How many of those are independent? Do I have to estimate all 8, or can I get away with fewer? They have to sum to 1 also, right? They do, if you add up all the columns. So I guess there's 7 independent ones, and then the 8th one I can just get as 1 minus the sum of the others. Okay, so if we're doing this conditional distribution, it looks like maybe we save a little bit here. Let's look in a little bit more detail at that. So suppose in general, we're trying to learn the probability of y given x. Ooh. we want to get P of y given x. And by the way, you see here I'm introducing a notation we will use frequently in the course where x in this case is actually a whole vector of variables. So random variables can be pretty much anything. They don't have to be just Boolean 1, 0 values. You can have random variables that are real numbers, like the temperature. You can have random variables that are vectors, and we'll just, and then of course the value of that vector valued random variable is a vector of values. So anyway, suppose we're interested in getting P of y given x, where x is just a vector of Boolean random variables, and y itself is a Boolean random variable. Then in general, if I want to estimate this and I have n Boolean x's and 1 Boolean y, how many parameters will I need to estimate? 2 to the power of n? That looks pretty good to me. Why?
Each one of them can have 1 or 0 as a value,
Mm-hmm.
and then all together it will be 2 to the power of n of them, right?
Good. So exactly. So if all the x sub i's can be a 1 or a 0, and I have n of them, there will be 2 to the n of those. If I'm going to build a table with a different row for each potential value of joint assignment of the x's, then there will be 2 to the n rows there. And let's see, I have to estimate both the probability that y equals 1 and the probability that y equals 0. But that's OK. Those are dependent, as we just agreed here. So I actually only have to estimate 1 parameter per row. Here, n equals 2. So I have 2 to the n, 4 rows. I have to estimate these 4. I don't have to worry about these because they're just 1 minus that. Right? OK, but I still have this 2 to the n problem. And as we talked about last time, even for small numbers, very small vectors, like only 30 features, if there are 30 Boolean features, it's still a billion rows. So it's still pretty explosive. It's exponential in n. So most of today is really about the question, how can we design a learning algorithm that estimates probabilities, but it does it in a way that's actually feasible. Feasible in the sense that we could train a classifier with only 150 people, like the people in this room, 150 examples, like the people in this room. And so we're interested in what kind of assumptions we can make or reformulations we can do that reduce the number of parameters down to the point where a reasonable amount of training data could be used to train it. Okay. So Bayes' rule is going to play a key role. And again, I want to use this slide not just to remind you of Bayes' rule. I'm sure you've got it memorized by now. But also to make clear the exact meaning of these kind of expressions. So when we say something like P of y given x, of course, y and x are random variables. They can take on many values. So when we put up an expression like that, what are we really meaning? What we're really meaning is this, to be more precise. What we mean is that if you think of all the values y can take on, all the values x can take on, then what that statement really means is for all values yi and xj that they can take on, the probability that y has this particular value given that x has that particular value is this. And I know that sometimes when people start manipulating these kind of expressions, it's easy to, every once in a while, kind of do a double take to try to remember what that means. I find it very useful to often, if you get confused, you can always bail out to just writing down this expression, and then now it's all in terms of very specific values. Okay, so Bayes' rule we could use, and Bayes' rule shows us if we're trying to estimate P of y given x, maybe it would be cheaper to estimate those 3 distributions on the right instead of that one on the left. Maybe we can get away with less than 2 to the n. So let's try that. If we're going to represent learn P of y given x instead by learning P of x given y and P of y, notice I'm not even saying P of x. Why? Because if I have suppose y is Boolean, and I want to know is it more probable that y equals 1 or y equals 0, it's enough just to look at the numerator because the denominator doesn't depend on y. The other way to say it is P of x can be replaced. P of x is just equal to the sum over all the values y can take on of this expression. And so if we just estimate P of x given y and P of y, we can use it to calculate the denominator too. Okay, so if we want to get this, what we really need to estimate is this and that. Okay, so how many parameters do we need to get this? Remember, y is Boolean and x is Boolean. Two to the n minus 1. So let's consider the case where y equals 1. When y equals 1, then we're just trying to get the probability of the x's given y equals 1. Then how many parameters do we need? 2 to the n minus 1, right? Right? Because when y equals 1, x is this vector x1 through xn. There are 2 to the n possible values. So we really need 2 to the n terms. Oh, but they sum to 1. So we don't, the very last one we don't need to estimate. We can just subtract the others from 1. Okay, and similarly, when we want to estimate P of, then also that'll take 2 to the n minus 1. And so we're actually going to need right? Is there something we can do here because they sum to 1? No. We can't tell anything about the probability of x given y equals 0. Once we know x given y equals 1, there's no calculatable thing there that has to sum to 1. So we really do need that many. And how many parameters do we need for this? 1. It's like a coin flip, right? It's a Boolean variable, Bernoulli distribution, 1 parameter. Okay, so we need that many parameters this way, whereas before we only needed 2 to the n. So actually Bayes' rule makes it worse. Right, this is bigger than if we tried to just estimate this, we'd need 2 to the n. Now we're going to need more. Okay, so that's not helping. But now here's actually what we can do and what we will do today to get a workable Bayesian classifier called naive Bayes. We're going to make a very dramatic assumption that the probability of all the x's given y can be expressed as just the product of each x individually given y. Okay, so like Oh, remember, well, let's take wealth and gender. Y was wealth, gender and hours worked were our two x's. So this is like saying the probability given wealth, that's y, of having a particular value for gender and hours worked is just the product of the probability given wealth of knowing the gender, of having a particular gender, times the probability given the same wealth of having a certain number of hours worked. Okay, so sometimes it's a reasonable assumption, and it is the basis for naive Bayes. In fact, naive Bayes is itself a kind of representative of a whole family of algorithms called Bayesian networks or graphical models. And like the others in that family, naive Bayes is based on a key notion called conditional independence. So conditional independence is just as important to the course as maximum likelihood and math. By the end of this class, you will have the three most important probabilistic notions in the whole course. So let's look at conditional independence. Conditional independence is defined this way. Given three random variables, x, y, and z, we could assume, to make it simple, that they're Boolean, but they don't need to be. They could be anything. We'll say that x is conditionally independent of y given z if the probability distribution governing x is independent of the value of y given the value of z. So put another way, for all the values that x, y, and z can take on, the probability that x will take on that value, given that y and z take on these values, is exactly the same as the probability of x if we only know z. In other words, y doesn't matter once we know z. Y is conditionally independent. Sorry, x is conditionally independent of y given z. Okay, so, and we'll often write it this way without the quantifier. Just say the probability of x given y and z equals the probability of x given z. And here's an example. Think of three random variables. Could be true or false. We could have just heard thunder, yes or no. It could be raining, yes or no. We could have just seen lightning, yes or no. You and I know, because we live in the 21st century, that lightning causes thunder. And therefore, it really doesn't matter whether it was raining, does it? So given lightning, it really doesn't matter whether it was raining. The probability of hearing thunder, given that we know whether there was lightning and whether there was rain, is just the probability of thunder given that we know whether there was lightning. Okay. Now that's not to say that the probability of thunder is independent, that thunder and rain are independent. They're not independent. In general, if it's not raining, you're less likely to hear thunder. And if it is raining, you're more likely to hear thunder. But if you also know the value of lightning, then all of a sudden, rain doesn't give you any additional information. All right? Everybody happy with conditional independence? This really matters. Okay. So how can we use this conditional independence assumption? Well, there it is. This is our definition of conditional independence. That's what we just wrote down. Here we're saying that x1 is conditionally independent of x2 given y. And one of the implications is that we can express this quantity in a nice way. So remember, the chain rule tells us that we can rewrite anything like this as just p of x1 given x2 and y times p of x2 given y. So this is just the chain rule. No assumption there. But now, you see this term is that term. And so if we make the conditional independence assumption, we can replace this. Okay? So that conditional independence definition justifies writing anything of this form as just the product of these independent probabilities. And similarly, if we had an x1, x2, x3, then you can work out and see that it'll just turn out to be the product of this term times p of x3 given y. In fact, no matter how many x1 through xn's I put there, this would just be the product. Right? Product we'll often write this way. So now let's think about what this conditional independence assumption does to the number of parameters we have to estimate. It's a beautiful story. Without the conditional independence assumption, you just told me that we would need 2 times 2 to the n minus 1 plus 1, I guess. 1 for this. If we have the conditional independence assumption, then how many probability terms now do we need to represent this? So let's see, we're going to have n of these, right? I can be anything 1 through n. For each of these, x can be 1 or 0, y can be 1 or 0. Let's take y equals 1. When y equals 1, we just need the probability that x equals 1. We don't need x equals 0 because that's just 1 minus. And when y equals 0, we'll need to estimate the probability that x equals 1 then too. So for each of these x of i's, we'll need 2 parameters. The probability that it's 1 given that y equals 0, and the probability that it's 1 given that y equals 1. So we get away with 2 then, 2 times n. And of course, we still need the 1 for p of y. But this is beautiful. Remember when we had 30 Boolean features and we were getting like 1 billion parameters here? Now we'll have 61. It's a wonderful world if conditional independence holds. Okay? So now we're there. Now we can talk about the first probabilistic algorithm in the course, naive Bayes. It works exactly like this. You all know Bayes' rule, which says how to calculate the probability of y given x in terms of those other terms. Conditional independence assumption, if we make it, allows us to re-express this term this way, just as the product of all of those. And now I can calculate, if I use my training data to learn those parameters, those 2n plus 1 parameters, then given a new example, a new x1 through xn, I can predict not only y, I can tell you the probability that y equals 1 and that y equals 0 given that new x, just by plugging in the values that I observe for x and calculating this. Okay? All right. So that leads to the following very simple algorithm, which you will get a chance to implement soon in the next homework assignment. To train a naive Bayes classifier, suppose we're trying to learn P of y given x1 through xn. In our old days, we would have said we're trying to learn the function from x to y. It's the same thing. Here's the training procedure. For every possible value y can take on, we need to know the prior. And for each value x can take on, we need to estimate the probability that x will take that on, that x sub I, feature x sub I, will take on its jth possible value, given that y takes on its kth possible value. And we need to know these for all the values that xi can take on and for all the values that y can take on. That's it. That's all the training is estimating these parameters. Then given a new x, what we do is we just say that the y value for the new x is just, this is just the numerator in Bayes' rule. It's just the prior on y times the product over all the features of the value of that feature in this new example, given that y equals yk. And we just pick the yk that makes that numerator of Bayes' rule the greatest. And if I use this notation for the parameters, like theta for the parameter I estimate for the prior, pi for the prior, and theta for these conditional ones, then this quantity is just, well, the prior is just my estimate that I got during training, pi k, and the conditional probabilities of the values of the x sub i's given yk's are just these. So classifying is just a matter of multiplying together those selected parameter estimates that happen to match the values of my new example that I'm trying to classify. Okay? And we can estimate those parameters using our old friend maximum likelihood. Okay, so let's try it. I want to train a naive Bayes classifier. Each of you is a training example or a test example. Let's say if you are seated on this last row next to the aisle, do not vote when we're collecting training data because you are the test examples. We're going to test out our trained classifier on the people who are sitting in the aisle here. I see people jockeying for position and for the last aisle seat there. Okay, and the classifier we will train is one that's going to predict whether you live in Squirrel Hill, given the variables g, d, and b. G is 1 if you have shopped at any time since September in the Giant Eagle that's in Squirrel Hill. If you don't know what the Giant Eagle in Squirrel Hill is, you haven't shopped there. Your evaluation is. D is 1 if and only if you drive to CMU or carpool to CMU. And there, let's say, if you've done it at least, 10 times since September. B is 1 if your birthday is before July 1st and 0 otherwise. Okay, so those are 3 features from which we're going to train a classifier to predict whether you live in Squirrel Hill. Okay, now, the first question is, well, what are the parameters that we're going to have to estimate here? And then we're going to vote with a show of hands and collect the statistics using advanced parallel processing. Okay, so what are the parameters I need? Remember, I need the priors on y, and then I need all the p of x sub i's given y's. Okay, so I'll start. It's easy. For the prior on y, I just need to know the probability that y equals, y is s in this case. So I'm just going to want to know the probability that you live in Squirrel Hill, and the probability that you don't. I need to know both of those. Of course, this is just 1 minus this one, so we won't have to do this twice. And then for G, for this one, what will I need? For P of G given S, I'm going to need a bunch of terms, right? I need P of G equals 1 given S equals 1. I need P of G equals 1 given S equals 0. Right? I need that as an additional one we're going to estimate. I can't calculate the second one from the first one, but I can calculate from this first one, I can get P of G equals 0 given S equals 1, right? Because those two in that row have to sum to 1. So I'm putting over here the ones that I really have to that we're going to have to really collect statistics on to get. And over here, ones that we get for free because there's a sum to 1 thing. Okay, so I could go on writing, but better than my handwriting is this. Okay, so we're going to have to collect all these statistics, 1, 2, 3, 4, 5, 6, 7 numbers. These we don't have to collect because 1 minus this equals this. Okay? All right, now, some of you are used to sequential processing. We're going to do parallel processing. I would like everybody in this row to just stand up. You're the dividing line that will make our counters have an easier time. Okay, sorry, you're going to have to stay standing while we're voting. Ahmed, would you like to count the left? Oh, we could do one. How many counters do we have? Okay, we have 4 counters. So let's go halfway back, and that row can stand up too. Yeah, let's say that row, that's fine. Okay, good. So each of our counters, please go to 1 quadrant. You'll see this is a Hadoop-like process for parallel processing. Okay, now if you're standing horizontally, you belong to the front half, okay? Vote with the front half. Oh, it doesn't matter, but counters, the people who are standing, count them as front, okay? And if you're counters, for the people who are standing here, count them as that side of the room, okay? So we don't want to double count the standers. You're just marking a line. Okay, so now we can do this. So let's start with, first we need to know how many people there. Okay, everybody count your quadrant. How many people are there? Okay, standards are going that way and this way. So it's 1, 2, 3, 4, 5, 10, 15, 16, 17, 18, 19, 20, 21, 22. Okay. All right, so I have 22 in this quadrant. Nina? Still counting. She's a theoretician.
Well, I assume that this is noise tolerant, the classifier. I hope it's noise tolerant.
It is, yeah, we're hoping. How many?
Who's in the test set?
Oh, the test set is this group.
Just the N.
Oh, thank you for pointing that out. I had to remove you. Oh, and I had to remove the 4 of you. Okay, so how many back in that quadrant? You got 32?
33.
33?
So 22 excluding the people
Good.
in the N.
And
I think 29.
how many?
29.
29? Okay. All right, so that's our N. Okay, now raise your hand if in fact you do live in Squirrel Hill and you're not a test example. Okay. You're hers. Okay. How many?
7, I think. Yeah, 7.
7? Including her, right?
Yeah.
Okay. Okay, Ahmed? 10? And?
4.
4? Okay. All right. And so that means 12, 24. Let's use maximum likelihood estimates. And so we have 55, 65, 73, 93, and 9.
It's 26 though.
Did I get the right? 55, 75, 84, 94, 102. Okay. And so the rest of you, I assume, do not live in Squirrel Hill. 26. Okay, I'm a theoretician. Okay. Now, if you do live in Squirrel Hill and you drive or carpool to CMU, at least with some frequency since September, raise your hand. Wow. Okay, total? 1, 2, 0. Okay, so that's 1 plus 2 is a total of 3 out of 102. And so the probability of not being that is 99 out of 102. Okay, and if you do not live in Squirrel Hill and you drive to work or carpool to work, raise your hand.
Shouldn't it be 3 over 26?
Oh, thank you. Wow. You guys are better at, thank you. Okay, if you do not live in Squirrel Hill, but you drive or carpool to work with some frequency, raise your hand.
I have 1 here.
1? Really? Just 1 in the whole room? This is a bad feature. Okay. Oh, man. Okay. I should have picked... Okay, you know we're going to have unreliable estimates with these counts. Okay, now if you do live in Squirrel Hill and you shopped at the Giant Eagle at least once in September, raise your hand. 1, 2, 3, 4, 5. Okay? 8. 4. 9. Okay. And that's out of 26. And if you do not live in Squirrel Hill, but you shopped at Giant Eagle, raise your hand. You must not be living at Squirrel Hill, but you shopped in the Giant Eagle, which is in Squirrel Hill. Okay. 6, 7. Okay. We will not share this data with Giant Eagle. 11? 11 for Nina, 11 from Ahmed, and 8. Okay, and finally, if you live in Squirrel Hill and your birthday is before July 1st, raise your hand. 1. 4. 2. 5. 2. Okay, and finally, if you do not live in Squirrel Hill and your birthday is before July 1st, raise your hand. 3, 4, 5. 7 from Nina? 8? 6. It's remarkable. More people were born in the second half of the year if you take machine learning. Okay. All right. So now we have, you just trained a naive Bayes classifier. That's all you need to do. If you have a set of data, that's all you need to do. If you want maximum likelihood estimates, remember, that's just like taking the alpha over alpha plus alpha 1 over alpha 1 plus alpha 0. That's what we were just doing. And we're doing that for the priors on S. And then for the conditional probabilities, we did the same thing, right? We counted the fraction of b equals 1s and b equals 0s given S equals 0. So these are simply maximum likelihood estimates. And we have now trained our naive Bayes classifier. Okay, now, what we would like to now do is apply this to some test examples to see how well it classifies them. I don't know whether during that training process there was time to interview the test examples or whether we need to do that now.
I did not pay attention to that.
Okay, good. So now we need to interview the test examples. Test examples, could you simply write down, do you have a piece of paper? Could you just write down on one piece of paper the 3 values for U, for D, B, and G, and secretly for S too, although we won't look at that until we predict it. Okay, so we need your 4 variables. And you can just pass them down this row. And when they come here, our master calculator, Nicole, will use these numbers to make predictions. So we'll come back and we'll see how that worked. Okay. So now let's move ahead. We'll come back. Oh, you need those numbers. Okay, that's good. That's good. Yeah, we may as well. I calculated this one wrong. While we're working out that data, there are a couple subtleties of naive Bayes that I want to bring up. The first one is this conditional independence assumption. It's kind of it's a very convenient assumption to make, but it's actually not true in a lot of cases. And it turns out, nevertheless, naive Bayes classifiers are very widely used. In fact, if somebody gives me a new data set and asks me, should we work on this? Is there any hope for learning from this data set? Quite often, naive Bayes is the very first method I just try on it. Because it's so easy, you just saw how easy it is to train a classifier. And even if the conditional independence assumption is not fully satisfied, quite often it'll produce at least signs of life, some kind of result that's not bad. But it is true that if we have variables that are not conditionally independent and we make that assumption, then we're misestimating the real probabilities involved. And so, are we okay? Okay. So, for example, in the extreme case, we might have, suppose I had made up two variables. B1 for is your birthday after or before July 1st, and B2 for is your birthday after July 1st, or July 1st or later. If I made up those two, you would know, oh, those are actually identical variables. And if we had used those, then obviously they would not be independent. If I know whether you were born before July 1st, I know the answer to whether you were born after July 1st. They'd be identical in some sense. And so what will happen in that case is that when we're going to get our probability of y given x, which we're going to calculate as the prior on y, let's say, let me write it this way to make it a little easier to see. Say the probability that y equals 1 given x. I'm just going to do that and more of those. I'm going to, if x1 and x2 are actually copies of each other, what I'm going to end up doing incorrectly is using that probability twice. And it will get to kind of it'll have an inordinately heavy say in the final probability. If they're really independent, then each feature deserves a vote in this product, which is going to give us the final probability. But if in fact two of those things are identical, meaning they're not conditionally independent at all, they're just one and the same variable, then you can see we'll actually end up giving it twice the emphasis that the other variables will get. And if things aren't exactly identical, but they are at least dependent on each other, like I could ask, is your birthday before July 1st? I could also ask, is it before September 1st? Those are not identical variables, but they're clearly dependent. And so in that case, it will still be the case that we'll end up kind of overemphasizing those two variables taken together. And so as a result, it kind of, well, that's one of the subtleties of naive Bayes. And despite that, we often get reasonable classifications. In fact, there's a kind of interesting paper by Pedro Domingos and Mike Pisani some years ago pointing out that the reason we can often get good classifications is that we don't actually, the conditional independence assumption, if it's violated, might give us incorrect probabilities. But if we're going to finally just classify our example by saying y equals 1 or y equals 0, then the only thing that matters is whether we got the probability on the right side of our 0.5 threshold. And even if we misestimate it by some amount, as long as it ends up on the right side of the threshold, we will correctly label that example. Okay, so that's one subtlety. Another subtlety which is almost showed up surprisingly when we were doing this classifier, although I didn't think it would, is we can have features that are so rare that we end up getting 0 counts. So I was shocked to see so few people, we almost had a 0 count for, I think, Drive from Squirrel Hill. But for example, what if I had a feature like the exact date on which you were born? Then if we trained on everybody in this room, we don't even have 365 people And there'll be a lot of dates. And if I include the year, then there'll be even more zeros. So in that case, when we train the naive Bayes classifier, if we use the maximum likelihood estimate, we'll have a lot of terms like the probability that this x is 1, given that you live in Squirrel Hill. We're going to get a lot of zeros, because probably none of you maybe were born. If you were born on that day, happy birthday. It was yesterday. And so we can get zeros. Now, why is that a problem? That's a problem because, remember, the way we're doing this is by in this numerator, every one of those probabilities gets multiplied together. And so if our maximum likelihood estimate for this probability, if we estimate that's a hat to mean that it's an estimate, if we estimate that to be 0, then if we actually test our classifier on somebody who was born on a day different from the training examples, then there will be a 0 as one of these terms, because we estimate that's, in our maximum likelihood estimate, we got a 0. And so it's problematic simply because if we have 1,000 features here we're using, it only takes one of them to be 0 to give us a 0 here. And so sparse data and maximum likelihood estimates of 0 are a big problem for us. So how can we get around that? Suggestions? You know the answer.
We can use prior.
Use what?
Prior.
Yes, use a prior. Instead of using a maximum likelihood estimate, like we just did, we could use a map estimate and put a prior. Let's hallucinate some examples and add those in in the form of, say, a beta prior or a Dirichlet prior, which is the generalization of the beta prior to variables that aren't Boolean but take on arbitrary number of discrete values. And in fact, that's exactly the solution. So we want to use map estimates. So for example, we could add in one hallucinated example for every birthday that's possible. Just imagine a count of 1 for everybody, for every possible birthday. And then we'll superimpose on that the actual observed data. But that way we won't get any probabilities that are exactly 0 because our map estimate, notice we'll never do that, right? Because we're adding in even one hallucinated example per value of x sub I is sufficient to keep us to not have exactly a 0 estimate. Okay, so let's see, Nicole, how are we doing on our calculations?
Calculations are fine.
Shall I just call out when I should come back to you? How's that?
What do you want? What numbers would you like?
Oh, okay. Well, let's see. First of all, how many test examples do we have?
10.
Okay. Can you read me out the, let's say, probability that they live in Squirrel Hill for each of them?
Oh, the probability that they scroll up for each of the test examples?
Yeah. Or if you don't have that, if you just,
I do.
okay.
Probability that they do live in scroll. Okay, so, well, so for number 1, it's 0. So have a 0 somewhere, right?
No, no. We had a 1 out of 76.
I thought we had a
Isn't there a
26 out of 26,
Yeah.
which would lead to a 0.
P of G equals 1 given its equivalent? So that would make P of G equals 0, S equals 1.
Which means that if they don't,
Oh, man.
which means that if they don't stop at Giant Eagle, that leads to a 0 probability that they live in Squirrel Hill, right?
Wow. Okay. Well, we did get that problem. Thank you. This is horrible. Okay. But here it is. So this is 0 out of 26. Boy, I wish we had used a map estimate. Okay. So the probability for number 1 is 0. Oops. Okay, the probability that S equals 1, that they live in Squirrel Hill given their particular values, is 0.
Yeah.
Now we can infer that they must live in Squirrel Hill but not shop at Giant Eagle.
So for number 2, it's 0.37. For number 3, it's 0. For number 4, it's 0.37. For number 5, it's 0. For number 6, it's 0.41. For number 7, it's 0.37. For number 8, it's 0. For number 9, it's 0.37, and for number 10, it's 0.
So there are 5 people in this class who live in Squirrel Hill and do not shop at Giant Eagle, and they're all sitting on this row, on this column?
No, I mean, these people don't necessarily live in Squirrel Hill, right? They just don't shop at Giant Eagle in Squirrel Hill.
No, that should not do it, right?
Oh, well, maybe I made a mistake then. You're saying there should be, I feel there should be a 0.
Yeah, if they satisfy that they live in Squirrel, oh, I see. You're right.
What's the, am I right? I don't know. Why don't I go through and just double check? that
Okay. Okay. All right, we'll come back.
I did this correctly, and then we can go back.
Okay. We could make this another homework assignment. We could just publish the statistic. Okay. All right. So, okay. So the 2 subtleties of naive Bayes. One we did see, I just didn't recognize it, is that we accidentally got a maximum likelihood estimate of 0 for the probability of not shopping at Giant Eagle if you do live in Squirrel Hill. And because of that, that gives us a probability of living in Squirrel Hill of 0 if you do not shop at Giant Eagle. So that is correct. That doesn't mean that the people. Notice in those examples we did not ask what was their correct label. I'm hoping that the 0s were actually people who do not live in Squirrel Hill. So that could be exactly right. Okay, but and then the second subtlety, and the way we deal with the first is we often use map estimates instead. Second subtlety is that conditional independence is really a very strong assumption, and it may not be satisfied even in our case. So it might not be true that whether you carpool and whether you shop at the Giant Eagle in Squirrel Hill, it might not be the case that those are conditionally independent, given that you live in Squirrel Hill. I don't know. Okay. All right, so let's move on and let's begin to see how we would apply naive Bayes to you know, I'm looking at the clock and I'm seeing we're going to run down. So what I want to do is, instead of starting this, I'll just say next time we're going to look at naive Bayes applied to classifying documents, which you will also get a chance to look at in the homework. And maybe we can just come back to our data. Now that I think it through, I can see that those zeros sound like well-founded zeros. Those are actually the probability that you live in Squirrel Hill. Given, and I guess those were all people who did not shop at the Giant Eagle, and that's why our classifier assigned them 0 probabilities. So now I want to, before we end, I want to ask what their actual true values were. So the truth for, can we get the truth, Nicole, for example 1?
Okay, so Lawrence, hold on. I think I figured out.
Or do you want to?
She's collecting those one problem. I have a question, Dominica.
Uh-huh.
So the paper that you mentioned by, I guess, Domingos, what type of data did they look at? Well, they made the claim that, you know, naive Bayes assumption is not such a bad assumption, but on what type of data? Is it text data, image data? Because on image data, like on raw pixel,
Yeah.
it's expected to not be very,
Yeah, that'll be pretty.
it's been part of being true, right? So what type of data did they look at?
Yeah.
And also what I mentioned,
So they were giving a kind of informal argument and then testing over a variety of data sets and showing.
because that's
I don't think they were using image data.
because I can see it being true in like
Yeah.
text data, but image data, like when you use pixels, it's actually
That'd be much worse. Although we use it for brain image data classification, it's ridiculously good, even at the pixel level. So Nicole, should we come back to this on Wednesday or?
No, I feel like there must be a mistake because the people. I don't know. I'm sorry. It's like,
Okay, so let's do it at the beginning of class. Next time?
there shouldn't be zeros unless
If they,
unless it's like
if G equals 0, you're going to get a 0.
G equals 0, you'll get a 0.
Yes.
G equals 0, but S.
But you don't know S when you're classifying.
So
So
I think I did.
I think you did it right.
Okay, so then it's
Okay, all right, the results are now ready. This is important because it's possible that the whole, no, I don't want to make that. Here come the results. Okay,
people that number 4 and number 7 live in Squirrel Hill, and the other people do not.
number 4 and number 7 live in Squirrel Hill.
Yeah.
And the rest of the people do not. Okay?
Yep.
And so now we can ask, how accurate is our classifier? We can ask this 2 ways. We can ask, what fraction of the examples did it correctly classify? And the answer to that is 80%, because it assigned a probability less than 0.5 for every single one of our 10 test examples. And it turns out 8 of them, it correctly, therefore, classified as a 0. So it's 8 out of 10, if we look at it that way. Some of you are smirking because you might be thinking, oh, but you just say no is not a very good classifier. So we could, a more subtle way is to look at the misassigned probability mass. Right? So, and these are in fact 2 different ways that we often do measure the accuracy of classifiers. One is just a simple, what fraction of things does it correctly label? 8 out of 10 in this case. But if we ask, well, what about the misassigned probability mass? By that I mean, for this one, it assigned 0 probability that they live in Squirrel Hill, and therefore probability 1 that they don't, and that was correct. So there was no misassigned probability mass. This one, it misassigned 0.37 that they do live in Squirrel Hill. In fact, they don't, so we would penalize at 0.37. This one, it misassigned 63% of the probability mass, so we could count it that way. But, so without doing the detailed arithmetic, I just will point out that the 2 cases where people did, in fact, live in Squirrel Hill were at least non-zero probabilities, meaning that they didn't live in Squirrel Hill and refused to shop in Giant Eagle. And so they were at least, if we rank order the examples from most to least probable of living in Squirrel Hill, this would be most probable, incorrect, but then these would all be tied for second place, and it includes the two that, in fact, do live in Squirrel Hill. So I would say by either measure, this is not too bad. And therefore, therefore you should definitely come to next class. See you then.